This is problem set number 2, problem 1. Helium gas with a volume of 3.2 liters under a pressure of 0.18 atm and at 41 degrees Celsius is warmed until both pressure and volume are doubled. For part A, what is the final temperature? And for part B, how many grams of helium are there? The molar mass of helium is 4 grams per mole. Let's write down the givens and the equation, or in the problem. So we have volume is 3.20 liters. Pressure is 0.180 atm. And the temperature is 41.0 degrees Celsius. And these initial values, so actually that's V1, P1, and T1. So these initial values are warmed up until both pressure and volume are doubled. So that's saying that in the end, the pressure and volume are doubled. So P2, the final pressure, is equal to double the value of P1. So is equal to 2P1. And same thing with volume. So the final volume is twice the initial volume, 2V1. Okay? And what is the final temperature? That's for part A. Okay? So part A, what is the final temperature? Okay. So in this problem, I will use the ideal gas law equation, which is PV equals nRT, right? And that is, here we have pressure. This is pressure. This is volume. This is the amount of gas. And the unit is moles, right? And this is the universal constant R, universal constant. So it doesn't change, R doesn't change. Actually, I'll also write down the value of R. I'll write that, and then this is temperature, right? Okay, anyways, so the value of R is 8.31 joules per mole times Kelvin, okay? So that's one way to write it. Another way to write it, which is also equal to that, but in different units, is 0.08206 liters times atm over mole times Kelvin. Right, and the value of that is equal. And I guess the determination of which R to use, right, whether you're going to use this one or this one, that would just depend on which units are given in the problem. So right here I've got liters, ATM, so I'll likely use this guy right here. Okay, all right, back to the problem. So I've got the ideal gas law equation right here, and I have values for P1, V1, and T1, okay? And if I solve this for N and R, I would get N and R is equal to initial pressure times initial volume over initial temperature, right? And I'm being asked to find the final temperature. So I'll just write down the ideal gas law equation, but for my final state. So final pressure times final volume is equal to the amount of gas the universal constant, and my final temperature. Okay? And this is a universal constant, so that's not going to change. The amount of gas is not going to change either in this problem, right? So I could solve for the amount of gas times R is equal to my final pressure times my final volume over my final temperature. And these guys are equal to each other. Therefore, these are also equal to each other. So, therefore, P1 V1 over T1 is equal to P2 V2 over T2, right? And I am looking for T2. In fact, everything else here is given. Oops. V1, I've got V1. P1, I've got P1. T1, I've got T1. P2, and V2. So at this point, it's just a matter of plug and chug, and I should be able to find T2. Okay? So T2 would be equal to P2 V2 times T1 over P1 V1, right? And then I could also substitute in P2 and V2 in terms of P1 and V1, right? So I'll do just that. So that is equal to 2P1, 2V1, T1 over P1, V1. And I can cancel things out, like P1 on top and P1 on the bottom, V1 on top and V1 on the bottom. And I'm simply left with T2 is equal to 2 times 2 times T1, right? And I know T1 is 41 degrees Celsius, so in Kelvin that would be equal to 314 Kelvin. Therefore, T2 is equal to, so that is equal to 2 times 2 times 314 Kelvin. And that is equal to 1,256 Kelvin. Or in centimeters, if I subtract 273, I would get T2 is equal to 983 degrees Celsius. So that is the answer for part A. All right. Now for part B, the question is, how many grams of helium are there? And we were given the molar mass as being 4.00 grams per mole. Okay. So for part B, we're looking for mass. And we were given that the molar mass is equal to 4.00 grams per mole. All right, again, I'm going to use the ideal gas law equation, which is PV equals nRT. Okay? And I am looking for mass in grams, and I know that I'm given this guy, the molar mass in grams per mole. Okay? So I know for both initial and final, I know the pressure, right? I know P1 as well as P2, right? I know V1 as well as V2, so I've got this. I also know T1 and I know T2. And I know that R is a universal constant and that doesn't change. So I can choose either to use the first state or the second state, the final state, right? In this case, I'll just use the first state. So P1, V1, and T1. And then I'm going to try to look for the amount of gas, which is in moles. Because if that's in moles, let's say whatever value is in moles, I know that this is going to cancel out, and then I'd be left with grams, right? Which is a mass. Then that's what I want. Okay? And by the way, I just chose to use the first, the initial state, but if I wanted to, you could also use the second, P2, V2, and T2, and you'd have the same R, and then you'd get the same value for the amount of gas in moles. So it's just a matter of choice. But I'll just use the initial conditions. All right, so I'm looking for N, so that would be N is equal to P1 V1 over R T1. Okay, and that is equal to 0.180 ATM times 3.20 liters over the universal constant, which, since I'm given liters and ATM for pressure, I will use this version of R. Okay, so that is 0.08206 liters times ATM over mole times Kelvin. Okay, and T1 is, I believe, 314 Kelvin. Okay, 314 Kelvin. All right, and if I plug that in the calculator, I would get that the amount of gas is 0.02235 moles. Okay, and again, I am given the molar mass right here for helium. So I would multiply the molar mass times the amount of gas I have in moles, and that should equal my mass in grams. Okay, now let's try that. So my molar mass is 4.00 grams per mole. And I'm going to multiply that by the amount of gas that I calculated right here. So that is 0.02235 moles. Okay, my moles will cancel out, so I'm left with grams. And if I multiply 4 by 0.02235, I would get that my mass is equal to 0.0894 grams. And that is the final answer for part B.